All right, get this. Byte-level language models. Doesn't that sound kind of like, we're about to step into some futuristic tech thriller?
Little bit, yeah.
Today we're diving into research on one called BLT, the Byte Latent Transformer.
Catchy name.
It is, right?
Mhm.
It's a mouthful, though. But the idea is pretty simple. What if, instead of teaching AI to read in, chunks like words or sentences, we went straight to the source, the bytes?
Yeah, it's about getting, as granular as possible. Think of it like most AI today is reading with those chunky toddler books. Big
Right.
picture, simple words.
Right.
BLT is trying to decipher the entire library, letter by letter.
Wow, okay. And the researchers think this could lead to, some wild improvements.
Mm-hmm.
AI that just shrugs off typos like they're nothing.
Mm.
Maybe even AI that runs smoothly on something as small as our phones because it's so efficient.
Yeah, potentially huge, huge gains.
You sent in this paper, so let's see if PLT lives up to the hype.
Okay, well, before we get into BLT specifically, we need to understand why this is such a big deal. Most AI models today rely on tokenization. They break text down into those chunks we were talking about.
Okay.
And that creates limitations.
Okay, tokenization. Break it down for me. Why is that holding AI back?
Imagine trying to build a house, but you only have, those pre-made wall sections and roof pieces, right?
Yeah.
You're stuck with whatever the manufacturer decided was useful. Tokenization's kind of like that limits what the AI can build with language.
So it's like AI is stuck doing paint by numbers instead of freehanding a masterpiece.
Exactly, and that causes problems. Ever get frustrated when autocorrect just totally mangles a less common word?
Oh, yeah.
That's fixed tokenization tripping up.
Yeah.
Same with, weird formatting or typos, throws the AI off completely. BLT tries to solve this by using dynamic patches.
Dynamic patches. So is that where the byte-level stuff comes in?
It is. Instead of preset chunks, BLT groups bytes together on the fly. It's like deciding what size Lego bricks to use based on what you're building, right?
Oh, okay. I see.
Simple sentence, small patch, complex, scientific jargon. BLT grabs a bigger handful of bytes to make sure it captures all the meaning.
So BLT is reading smarter, not harder. It's like it can skim the easy stuff and then laser focus on the parts that need more attention.
That's a great way to put it.
But how does it know what's simple and what's complex? There's got to be some brain power behind that decision-making.
There is. It uses what's called an entropy model. It's basically a little AI sidekick that's constantly guessing how hard the next byte will be to predict.
Okay, entropy. That sounds like a physics term. How does it apply to language?
Think about trying to guess the next word in a song lyric. Sometimes it's obvious, sometimes it's a total curveball.
That's right.
That surprise, that unpredictability, that's high entropy. And that's when BLT says, hold on, things are getting complex. Time to start a new patch.
So if I'm reading, a technical manual and suddenly there's a bunch of jargon I'd never seen before, entropy spikes, and BLT knows it needs to pay extra close attention.
Exactly. It's like the text is sending up a flare saying, hey, things are about to get interesting. And BLT is ready to grab a bigger patch and really dig in.
That's pretty slick. But a fancy system doesn't mean much if it doesn't actually work right.
Right.
Did the researchers put BLT through its paces?
Oh, they did. And what's really exciting is that BLT seems to be as accurate, if not more so, than the token-based models. But here's the kicker. It uses significantly less computing power to do it. We're talking up to 50% less.
Whoa, hold on. Same result, half the effort.
Pretty much.
That's like finding out you can get the same workout in half the time at the gym. It's got to have huge implications.
It does. Think about the potential. Right now, super powerful AI needs those massive data centers, tons of energy. But what if we could achieve that same power with a fraction of the resources? It could make AI way more accessible, not to mention more sustainable.
This is starting to feel like a total game changer.
Right.
We haven't even touched on BLTs, like apparent resistance to typos and other things that would, trip up normal AI.
Oh, that's right. BLT seems to be incredibly robust. They threw all sorts of messy, error-filled text at it, and it just shrugged it off, still understood the meaning perfectly. It's like BLT is reading between the lines, not just focusing on the literal characters on the page.
Yeah, I'm picturing BLT like some cool laid-back detective who can solve the case even if the clues are, scattered and half legible. And all this just from reading at the byte level. Color me impressed.
But we've covered a lot of ground already. I think it's time to take a step back and let this all sink in before we jump into the really the nitty-gritty details of how BLT works its magic.
Sounds good to me. There's a lot more to unpack here, especially when it comes to the technical details of BLT's architecture and how it compares to those traditional models we've been talking about. All right, we'll be right back to continue our deep dive into BLT. Don't go anywhere. Welcome back. Before the break, we were getting pretty hyped about BLT's efficiency and how it just breezes past typos and other methy text. BLT was built for the real world where things aren't always, perfectly formatted and grammar isn't everyone's strong suit.
Yeah, it's true. BLT seems remarkably unfazed by the kinds of errors that would, send traditional AI models into a tailspin. But what's even more remarkable is how this byte-level approach could change the game when it comes to scaling up AI.
Now, you mentioned something earlier about a byteifying process, taking existing AI models and, I don't know, sprinkling some byte magic on them. I got to admit that piqued my curiosity.
It's a fascinating concept, and the researchers actually put it to the test. They took a large existing language model called Llama 3.1. This one's based on the usual token approach, and they used its knowledge to give BLT a head start.
So it's like they took the training wheels off Llama and used them to build a supercharged BLT.
Yeah, it's a great analogy. They essentially transferred the parameters, the learned information from Llama to the core processing part of BLT. Then they continued training BLT, but with a much lighter touch on that core part, letting it focus on adapting to the byte level.
And what were the results? Did this Franken model, this BLT-Llama hybrid, actually work?
It did. And get this bytified BLT actually outperformed both the original Llama model and a BLT model that was trained from scratch, all with roughly the same amount of computing power used for training.
So we're not just talking about building a better AI from the ground up. We're talking about potentially upgrading existing AI to be more powerful and efficient. That could change the entire landscape of AI development. No need to start from zero every time.
Exactly. This byteifying process opens up so many possibilities. Imagine taking the best aspects of current AI models and, infusing them with the robustness and efficiency of BLT. It could accelerate progress dramatically.
Okay, now I'm really starting to see the bigger picture here. BLT isn't just a cool new model. It's a potential paradigm shift for the whole field of AI. But I want to go back to something you mentioned earlier about scaling. Because if BLT is already outperforming other models while using less power, what happens when we make it even bigger? Does it just keep getting better?
That's the million-dollar question, isn't it? And to answer it, the researchers did a deep dive into BLT scaling abilities. They wanted to see how it performed as they increased both the model size and the size of those dynamic patches.
Hold on. Bigger patches, bigger model, wouldn't that mean it needs way more computing power? It seems like you'd be going in the opposite direction of efficiency.
You'd think so, right? But here's where things get interesting. Remember, bigger patches mean BLT is processing information in fewer steps. It's like taking larger strides, you cover more ground with each step, and this seems to offset the added complexity of a larger model.
So it's a balancing act. You're making the model more powerful, but also giving it a more efficient way to process information. Did this actually work in practice?
It did. They compared BLT to those standard token-based models, but they kept the computing power constant for a fair comparison. And they found that BLT started to outperform the token-based models once they had enough data to really learn from.
So there's a tipping point, a moment where BLT's unique architecture really starts to shine.
Exactly. And here's what's even more fascinating. As they scaled up to even larger models, that tipping point seemed to occur earlier in the training process.
So the bigger you make BLT, the faster it learns and the quicker it surpasses those traditional models. That's pretty incredible. What does that tell us about the future of BLT?
It's a strong signal that this patch-based architecture could be the key to unlocking even more powerful and efficient language models in the future. Imagine AI that can process information as quickly as we can read, but with the depth of understanding that currently requires those massive data centers. That's the kind of future BLT is pointing towards.
This is mind-blowing stuff. But we've thrown a lot of information at our listener today. Let's take another break to let it all sink in. When we come back, we'll wrap up our BLT deep dive with a look at some of the finer details of how it works and what limitations the researchers identified. Stay tuned. And we're back for the final leg of our deep dive into BLT. Before the break, we were talking about how BLT scales up and its potential to revolutionize the world of AI. But even with all this hype, the researchers didn't just stop at, it works great. They wanted to understand why it works. right down to the nuts and bolts.
Absolutely, yeah. They did a series of what are called ablation studies. Essentially, they took BLT apart, piece by piece, like a super complex Lego model, right, to see which parts were truly essential to its success.
So they're playing AI Jenga, pulling out blocks to see what makes the whole thing collapse. What'd they learn from this?
Well, first they looked at that entropy model, that little AI sidekick we talked about. That helps BLT make those dynamic patches. They found that a bigger entropy model generally led to better performance, but there were like diminishing returns after a certain point. It's like you don't need an infinitely powerful sidekick. A reasonably capable one will do the trick.
Makes sense. Why spend extra energy on a superpowered sidekick when a competent one gets the job done? What else did they tinker with?
Well, they also experimented with different ways of actually creating those patches. Remember, BLT's innovation is that it makes them on the fly based on the complexity of the text. But they wanted to see how that compared to simpler methods like just grouping bytes into fixed-size chunks or even just using spaces as boundaries.
So back to our Lego analogy. They're testing if those pre-made wall sections and roof pieces could actually compete with the, dynamic build-as-you-go approach of BLT. What was the verdict?
No surprise here. The dynamic, entropy-based patching consistently outperformed the simpler methods, especially when it came to those like real-world applications of the model. It's like having a master builder versus someone who just follows the instruction booklet. The results speak for themselves.
Okay, so entropy is the secret sauce here. What about those other components of BLT, like the cross-attention layers that help it connect those byte-level and patch-level representations? Were they as crucial?
The ablation studies showed they were absolutely vital, especially on the decoder side, where the model is actually generating text. It's like those cross-attention layers are the bridge between the micro and the macro, between those individual bytes and the overall meaning of the text.
So it's not just about understanding the individual letters. It's about understanding how they all fit together to create words, sentences, and ultimately ideas. It's like BLT is reading with comprehension, not just decoding symbols. Did they mess with anything else?
Oh, yeah, they went deep. They even looked at different configurations for those local models, the encoder and decoder that handle the byte level processing. And they found that a surprisingly lightweight encoder worked best as long as it was paired with like a more powerful decoder.
It's like the encoder just needs to quickly package up those bytes, and then the decoder can take its time unpacking them and figuring out what they really mean. Sort of a division of labor, like a super efficient assembly line. What about those enogram hash embeddings? Those sounded pretty cool, but also a bit complex. What was the takeaway there?
They're definitely essential. The ablation studies showed that these embeddings, basically like extra layers of information about sequences of bytes, significantly improved BLT's performance, especially when it came to more structured or technical language. It's like they help BLT see the forest and the trees, the individual bytes and the bigger patterns they form.
It sounds like the researchers really put BLT through the ringer to figure out what makes it tick. But even with all this like meticulous testing and clever design, they acknowledge there's still room for improvement, right? Every superhero has its kryptonite.
That's right. They're very upfront about the fact that BLT is still a work in progress. One thing they highlighted is that the scaling laws they used to determine the optimal training regime were originally developed for those token-based models.
Right.
It's possible that BLT might benefit from a whole new set of scaling laws that are specifically tailored to its unique architecture.
So there's potential for even further optimization and improvement down the line. We might not have even seen BLT at its full potential yet.
Exactly. And even though BLT is more computationally efficient in theory, they admit that their current implementations might not be like as optimized as those for token-based models. There's still work to be done to make BLT as fast and streamlined as possible in practice. It's like they've invented this amazing new engine, but they're still fine-tuning the transmission to make it run even smoother.
And they're still working on that byteifying process we talked about, figuring out the best ways to leverage the knowledge from those pre-trained token-based models to give BLT a head start. It's like they're constantly looking for shortcuts to make BLT even more powerful and efficient.
And that's what makes this research so exciting. It's not just about a single model or a set of results. It's about pushing the boundaries of what's possible in the world of AI.
This has been an incredible deep dive. We've gone from the tiniest building blocks of data, those bytes, to a model that's challenging the very foundations of how we think about language and AI. I don't know about you, but I'm feeling incredibly energized by the possibilities. It feels like we're on the cusp of something truly transformative.
I agree. BLT is a powerful reminder that innovation often comes from looking at things from a different perspective. In this case, literally going back to the bytes. Who knows what other breakthroughs are waiting to be discovered if we're willing to challenge our assumptions and think outside the box?
That's a great note to end on. A huge thanks to our listener for sending in this fascinating research paper. And to all of you out there exploring the world of AI, keep asking questions, keep pushing the boundaries, and keep diving deep. Until next time.